Oh,
So,
okay.
like,
So you just want to show me your things?
Yeah.
All right, let me get my grade book out so I can put the points down.
I feel so stupid because I went to 203 and I saw this sign. And I went around there. I was like, "Where's room 219?" I forgot
That's our regular classroom.
I
huh?
should have thought that.
That's
first,
hilarious.
but-
That's hilarious. Okay, what did I do with my grade book? I know I brought it in here.
I'm sorry to interrupt everything.
No, it's all good. Just a moment. And what should I say? The Z. Yeah, well, that sucks. I know. When I was married, I was Zanazzi.
Oh.
So I went even further down in the alphabet. Okay, so you got goggles, notebook, let me check this.
I don't have the tabs.
That's all right, Just want to make sure you got everything. All right, you're good to go. Thank you. Make sure you take out your one. You can't take that.
Yeah, I'll leave the last time. Thank you.
You bet. All right, so here's how it's gonna go. I am recording this so that if you guys want to, you can look at it later. Since I didn't really record lab stuff last semester, I'm recording any applicable lab stuff now. There we go. All right, let's make sure that y'all can see this screen. I don't know how, sometimes it works really well with the lights on, sometimes with the lights off. Let's see what it's feeling today. Let's see here. All right. I think you guys can see that pretty good. Yeah, we are. Let's see. Whoopsie, that's no good. Let's see if this makes. Is that better? With more lights on or less lights on? Less is better. Does the light up here make it any better? I think it looks like it's a little clearer if I have my light on. All right. Oakley dokley. So take out the lab. Let's see. I'll pull the file up on my computer so you can look at the file here as well. And as you guys are working, I'll come around and take your points for the material screen. Hang on just a second, let me get this file really quick. I stopped. I'll lose track. Are you leaving? Is that why you want to show me now? What's that? Yeah. Okay.
Do you want the one down prior to the?
With my brown gray book, it's a really big thing. There it is. No. You should keep them until next week. I don't have the bin in here. Okay, here's how today's gonna go. Hopefully you've already done or are gonna do the pre-lab, which is, like I said before, this is the rules for ions, naming of ions. We're gonna go over that briefly for monatomic ions, but a lot of this is the polyatomic ions, and it gives you the sets of rules for the polyatomic ions. But once again, I'm not gonna make you know those rules. If you know the names, the charges, and the symbols of the 18 common polyatomic ions that I gave you, then you're good to go, okay? You don't have to know all these rules. You don't have to know the really funky, weird ones, you know, all these different odd things that you're not going to come into contact with. So you still need to do the pre-lab. You still need to complete it, right? But it's not something you're going to be tested on, okay? So don't let my disclaimer change your goal to make sure that you have the whole lab completed next week. Because next week when you walk in, you got to have the pre-lab done, the lab done. You're going to give it to me. Those 2 documents are only worth 10 points out of the 30 points possible. Then you're going to take a quiz on nomenclature, which is worth 20 out of the 30 points. So the lab itself is just simply the learning tool to get to the end goal, which is to know how to do nomenclature. All right? So just so everybody's prepared and knows what to expect, the lab itself is not 30 points. The lab itself is 10 points, and then the quiz is 20 out of 30. So y'all know, right? Okay, so the polyatomic ions, you all have a list in front of you, right, of the polyatomic ions. Everybody's got one of those. So those are the ones you're going to use in common. You also have the periodic table in front of you. And we're going to talk about the different types of compounds. Now, normally I have some visual aids that I bring in for this, but I think I can draw pictures on this sheet to give us the idea. What we're going to do is I'm going to give you an overview of nomenclature before we begin. Big picture overview. Then we're going to go by section. I'm going to give you the rules for that particular subsection. We're going to go through a couple of examples, and I'm going to turn you loose and give you 10 or 15 minutes to work on that section. Right? Then everybody will push pause again. We'll come back together. I'll give you the next set of rules on the next discrete section. You'll work on that for 10 or 15 or 20 minutes, right, after I give you a few examples with the people around you, and we'll go on like that, all right? I found that as a teacher, that seems to work a lot better than just dumping all the rules on you right at the outset and then turning loose on the whole lab, right? So if we do it little baby steps, a little bit at a time, it seems to make more sense. All right, so let's talk about an overview before we begin. And I get to tell you one of my most favorite lame jokes to begin the class session here today. Nomenclature. Definition of nomenclature. I don't know if you guys ever read the funny papers. Do millennials read the funny papers anymore? Anybody read the funny papers? Okay, I love the newspaper. There's something really tangible about opening up a newspaper and reading it. And ever since I was a little kid, I used to come home from school and I'd break out the newspaper. And my favorite thing that was always when I looked at the funny papers. Well, there was a comic called BC, which was a caveman that comes up to a rock. And on this rock, he has this big encyclopedia. And he looks up terms in the encyclopedia. And the definition of the terms is always kind of silly. They're not really the true definitions. They're kind of a play on words. Okay, so in one of the definitions in BC, the caveman walks up to a rock and he opens it up. And he's looking for the definition of nomenclature. The definition of nomenclature, according to the caveman, is a clature consisting entirely of women. Right? No men, clature. Laughter is appropriate at this point. Right? Okay. So nomenclature is not really a clature consisting entirely of women. That would be nice, but that's not really what it is, right? Okay, nomenclature has to do with how you put symbols or words together in the context of making meaning, like a language, right? In English, when we're talking about adjectives and verbs, we generally say something like the green frog. We put the adjective before the verb, or the adjective before the noun, excuse me, not the verb. We put the adjective before the noun. In Spanish, they say sapo verde, the frog that's green. Right? Okay, so they put the adjective after the noun in Spanish. Nomenclature in chemistry also has to do with the language of chemistry, right? How do you know What's the name of this stuff that you use probably almost on a daily basis in your kitchen or on your dinner table? That's the common name. The common name is table salt. But if you were going to use the IUPAC name, most people know the IUPAC name. And do you know what that stands for? IUPAC. That's the system that we're going to be using tonight. Anybody know what that stands for? Well, we should know. That stands for the International Union of Pure and Applied, I bet you can guess what the last word is. Chemistry, right? There is another set of rules that is, let's see, what do they call the other set of rules? And they involve Latin prefixes, and so we don't use that. We don't use the old set of rules. We use the IUPAC set of rules. So the International Union of Pure and Applied Chemistry, well, they came up with this set of rules to name compounds because a chemist in China has to be able to talk to a chemist in the United States who has to be able to talk to a chemist in Russia or Saudi Arabia, right? And we all have to have the same language. When we say NaCl, we need to know that it is sodium chlorides, right? So that's the common, or the IUPAC name for the common name that is table salt. All right, so when we talk about nomenclature, there's two basic big categories of compounds. There's ionic and there's covalent. And the rules are in two silos, and you can't mix between the two silos, because if you mix between the two silos of the rules, you're going to be using the wrong set of rules. Ionic compounds are probably about 90% of everything that you're going to come into contact with in your everyday lives and in the chemistry laboratory. Covalent compounds are maybe about 10% of what you come into contact with in the chemistry laboratory. These, unfortunately, or fortunately, depending on how you look at it, these are the easy peasy set of rules that everybody likes to use, but unfortunately that's only about 10% of the compounds. And these are the more difficult or hard set of rules, and that's about 90% of the compounds that you're going to come into contact with. All right? So let's talk about the differentiation, because you have to use a different set of rules for each kind of compound. The very first thing you do when you're trying to figure out nomenclature is you have to look at what it's made of and decide, is it ionic or is it covalent? Because if it's ionic, you use the ionic set of rules. If it's covalent, you got to use the covalent set of rules. And if you use the wrong rules for the wrong compounds, then the answer is going to be wrong. All right, so ionic compounds are metal plus a non-metal. Remember, if we look at the periodic table, we can divide up metals and nonmetals along this stair-step line. So the periodic table I gave you guys tonight doesn't have that stair-step line. So go ahead and add that. You start on the left side of boron, and you just make a little stair as you go down the periodic table. And everything on the left side of that stair-step line is considered a metal. Everything on the right-hand side is considered a non-metal. So that's the first super duper important differentiation between the different types of elements on the periodic table. So an ionic compound, you're going to pick something from this side, something from a metal side, and something from the non-metal side to make the compound. So that's the very first thing that you need to look at, is ionic compounds are composed of something that's metal and something that's non-metal. Covalent compounds, on the other hand, are non-metal plus another non-metal, or more than two. So that's a very different kind of compound. And there are a lot fewer of the covalent compounds because there's fewer choices, right? So if you're talking about an ionic compound, you got one of these and one of these. So look at all the different metals we have and all the different non-metals. Think of the different combinations, how many different combinations you could make if you take something from here and something from here and you add them together. There's hundreds and hundreds of combinations you can make, right? Non-metals, on the other hand, are limited. They're only the ones over here. So if you're talking about a molecular compound, also known as covalent, then you have to choose from the non-metal side. So the number of combinations you can make of all the different things on the non-metal side is much more limited than it is on if you're comparing ionic. So covalent compounds are also known as molecular compounds. Okay, so that's another way that you may see them described. All right, ionic compounds and covalent compounds, they both can be binary or ternary. Now, binary versus ternary. So either ionic and covalent can be binary or ternary. What do those words mean? Binary or ternary? Well, think about the word binary, right? A binary system is two. Okay, so binary thing is only two types of atoms. So you could have something that is NaCl, which would be considered binary. You could have something like CaCl2, which is also considered binary because it's only one of each type. Even though this one is a 1-to-2 relationship, it's still only one metal and one nonmetal, or two types of atoms involved. So if binary is only two types of atoms, what do you suppose ternary is? Well, more than two, right? Usually it's three, but sometimes you get some funky ones that have more than three. So more than two kinds. Oopsie, forgot an N there. Kinds of atoms. So binary compounds, one of the ways you can always know a binary compound, if, for example, you just get the name only and you don't know what the elements are and you've got to write the formula, binary compounds always end in IDE. So that's how you know that they're binary, because their suffix is IDE. Ternary compounds, both ionic and molecular, can end in ate or ite, generally. So those are the two suffixes that ternary compounds have. So ionic and covalent are very much separated based on the types of atoms involved in the bonding, but they both can be either binary or ternary depending on how many of each thing you have hooked up together. All right, so take your labs out now, and we're going to start the first section. All right, the first part of your lab looks something like this. You've got a big grid, and you're combining elements by using the rules for ionic compounds. So this first group of elements, you've got to use the rules for ionic compounds to write formulas for those elements. And you're going to put the name of the formula as well as the chemical formula in that box. Well, before we can start that, we have to talk about the common charges of ions based on their position on the periodic table. So let's look at the common charges of ions. We've got two kinds of ions we're going to be talking about. One is monatomic. The other kind is polyatomic ions. All right, so monatomic versus polyatomic ions. The name, what does the name imply for monatomic? Well, first of all, what's an ion? It's a charged particle. So a charged particle, how does a charged particle become a charged particle? What kind of pieces can it lose or gain to accrue a charge? Electrons. Electrons are the only ones that commonly move back and forth between atoms. So if it gains electrons, right, it's going to be what kind of a charge? It's going to be a negative charge, and we call that an anion, is the name we use for it. If it's going to lose electrons, what charge would it accrue? Positive charge. You guys know what we call those kind? Cations. Okay. So ions can be monatomic or polyatomic. So what does that prefix tell you about what's involved in the formula for the way that it's put together for that ion? Monatomic is a single atom that has become an ion, right? single atom. A polyatomic is a group of atoms that carry a charge. So they're both ions, right? But there's monatomic and polyatomic ions. I just gave you the list of polyatomic ions, the 18 that you should memorize. You need to know, of the polyatomic ions, you need to know not only their formula and their charge, but you also need to know the name. Here's one of the most common ones you will see in the chemistry, is nitrate. My advice to you is to make yourself some flashcards, because your life will be a lot easier the rest of this semester and into next semester in Chem 152 if you know the formula and the charge as well as the name of the 18 common polyatomic ions. So on one side of your 3x5 card, put the formula as well as the charge, and you got to know the charge if it's -1, or if it's something like carbonate, which is -2, you need to know that. And then on the other side of the 3x5 card, put the name. And then you can flip them back and forth. And studies have shown that if you want to memorize lists of nonsensical information that doesn't have a basis in your experience bank that you can relate it to, that 3x5 cards and short bursts of work towards memorization are the best. You can't sit down and say, I've got 2.5 hours today, I'm going to sit down, I'm going to memorize this list of polyatomic ions, right? It doesn't work like that. It works much better if you carry around the list of, or the 3x5 cards, and every time you have 5 or 10 minutes downtime, you're waiting in traffic on the red light, at the red light, instead of using your cell phone, pull out your 3x5 cards, right? You're waiting in line at the bank or at the doctor's office, like I'm always waiting for my mom at the doctor's office or the dentist's office, right? Pull out your stack of 3x5 cards and just flip through them for 5 or 10 minutes. You're brushing your teeth in the morning. Prop them up on the sink, on the faucet, right? And go through them for 5 or 10 minutes. You'd be surprised how easy it is to memorize a list of nonsensical information if you take it in little digestible chunks of 5 or 10 minutes at a time. Okay? That's my advice. All right, so monatomic and polyatomic ions, you can determine the monatomic ions based on your best and most favorite cheat sheet. Polyatomic ions is just a set of, you can either memorize the rules, which that's not my advice because there's too many rules. My advice is just to memorize the 18 common ones. All right, monatomic ions, you can determine their charge based on their position on the periodic table. Now we have some common families that we've already talked about in here. What's this group 1 family's name, this first group? Alkali metals. How many valence electrons does an alkali metal have in its electronic structure? Just the valence electrons, how many do they have? 1. Remember, metals like to lose their electrons, nonmetals like to gain them to achieve this octet, the octet rule. So this group of elements, the alkali metals, since they only have 1 valence electron, they lose that very readily. They become ions with a +1 charge. So I want you to put a little +1 at the top of that column to tell yourself that all the ions in that family, when they form ions, become +1 ions. Now, that doesn't mean they are always +1 ions every time that you look at them, right? That's a common misconception when we go through this unit, is I start giving you the charges of ions and people think, oh, lithium, sodium, potassium are always +1. No, that's only when they lose an electron. When the metal itself, the metal atom, is born in the Big Bang, and the original Big Bang and all the elements in the universe were created, they had all the electrons that they were supposed to have, right? If you find a hunk of sodium metal on the ground, it's going to have all the electrons it's supposed to have. It's only when it becomes an ion that it becomes a +1 charge. And here's my silly story to help you remember that. There's a commercial about a beer, Dos Equis beer, right? And they have the most interesting man in the universe as the spokesperson for Dos Equis beer. And what's the tagline that they always say about this most interesting guy? That he doesn't always drink beer, right? But when he does, he drinks Dos Equis. Okay, so they're not always ions. But when they are, they're ions with a +1 charge. Okay, so I'm using the same tagline so that you remember. They're not always ions. They're often atoms. But when they are ions, they're ions with a +1 charge. All right, this second group here, what do we call the common name of this second group here? Alkali earth metals. The alkali earth metals commonly have how many electrons in their valence shell? 2. So they like to lose those real readily, so they become ions with a +2 charge. Now, this group here, the alkali metals and the alkali earth metals, and there's only 4 other metals that only have a single ionic charge. Those 4 other metals that have a single ionic charge that you need to know for this class are aluminum, which is +3. So put a little +3 in the box that is aluminum. Zinc and cadmium are +2, which are right next to aluminum, but 1 down. And silver is +1. Every other metal. You guys have a highlighter? Does anybody have a highlighter in here? Borrow real quick. And if you have a highlighter, take it out. Oh, perfect. I always carried these around when I was a student. I was never without a highlighter. All right. So of the metals, these ones here, and these 4 are the only ones that have a single ionic charge. All other metals, everything that I did not highlight in yellow, all other metals can have more than 1 ionic charge. They sometimes become ions with a +1 charge. They sometimes become ions with a +2 charge. Some of them have only 2 or 3 ions that they form. Some can form up to 5 different kinds of ions. You can have a +1, +2, +3, +4, +5 of some of these atoms, all right? So the ones that are always only a single charge are these, and those 4. And that turns out to be super important later that we can differentiate, because we're going to have to incorporate Roman numerals for the ones that don't have a single ionic charge, right? All right, so those are the metals and the ones that always make a particular ionic charge. Let's talk a little bit about the nonmetals. Now, the nonmetals are a little different than the metals. Instead of giving up their electrons, most metals only have like 1 or 2 or 3 valence electrons. The nonmetals, on the other hand, have 5 or 6 or 7 or 8 valence electrons. Well, the noble gases, since they have 8, they hardly ever form ions. They hardly ever form compounds with anything else. That's why they call them the noble gases, because they don't interact. They have their octet already, so they're not interested in grabbing electrons from other atoms or giving away any of theirs, because they have their octet. What's this group here? Group 7A. What do we call 7A, the common name? These ones right here that start fluorine, chlorine, bromine, iodine. What's the common name for that group? The halogens. All right. How many valence electrons do the halogens have since they're in group 7? They have 7. So they're not going to give up all 7. What are they going to do to achieve their octet? They're going to grab 1 more. So all the halogens have a common monatomic charge of -1. So I want you to put a little -1 on top of the halogens so that you know that those always are ions with a -1. Now, they don't always form ions, right? But when they do, they form ions with a -1 charge. Oxygen, sulfur, those are the chalcogens, that group. How many valence electrons do they have since they're in group 6? They have 6. They're not going to lose 6. What are they going to do? They're going to gain 2. So put a little -2 up there. And then nitrogen generally is -3, and phosphorus is often -3. But then those are the ones that we know for sure they usually are. The rest of them can vary. All right, so that's the cheat sheet that's going to help you a lot with the monatomic ions. The polyatomic ions you should just memorize and learn on your own with some 3x5 cards. All right, so now if we look at this part of your lab, what they're doing now is they're taking baby steps to give you the idea of how to start using the common charges of monatomic ions to write nomenclature for some common compounds that they're giving you the negative and the positive charge for. So if you look at this first box here with Na and Cl, they're asking you to write the formula for Na and Cl when they come together as a compound. I already gave you that one, so I'll let you guys do that one. Let's look at the next one, Na and O. All right, if we were going to write the formula for Na and O, we'd say, all right, this is binary ionic compounds. Remember, binary ionic, the suffix is always IDE. So you use the name of the metal plus the name of the nonmetal plus the IDE suffix on the name of the nonmetal. So that's the convention. So if we're using that first example where we had sodium that has a +1 charge and oxygen that has a -2 charge, we've got to figure out what the nomenclature for this compound we call sodium and oxygen together. So your textbook, Brown and LeMay, will tell you to use this, what they call the crisscross method. And they tell you the crisscross method, you take the charges, the absolute value of the charges on the ions, and you crisscross them and make them into subscripts for the opposing ion. So in this case, we would write Na2O. And what that means is you have two atoms or ions of two ions of sodium connect to one ion of oxygen to make the compound sodium oxide. So we use the name of the metal, the name of the nonmetal, with an IDE suffix. So that's sodium oxide. So in that little box on this lab, what you're going to do in this box right here is you're going to put the formula Na2O, and then you're going to write the name, which is sodium oxide. Now, that's important to know how to do that, but the reason that this crisscross thing works is because all ionic compounds have a net charge equaling 0. They cannot have a net charge. They can't be like an ion with an overall charge and carry it. So the reason the crisscross thing works is Na has a +1 charge, O has a -2 charge. If we add just a +1 and -2, if that's all I use, then what would be my overall charge if I hook these two up together? +1 and -2 adds up to what? A -1, and that wouldn't work because ionic compounds have to have a net charge, an overall charge of 0. So that's why we have to have two of these sodiums in the compound formula for sodium oxide, because each one is +1 and it has to balance out the -2 charge of oxygen. Let's look at another one on this table here. Let's look at something like aluminum and selenium. Aluminum and selenium here. Okay, aluminum is +3 and selenium is -2. They're telling you on the table there. So if we look at aluminum and selenium, aluminum is +3, selenium is -2. We can do the crisscross thing again here. Take the absolute value of the charges of the ions and you crisscross them and use them as subscripts, so we come up with Al2Se3. Okay? So now, what would we call this thing if we're using our rules? Aluminum selenide. Not so bad, right? Name of the metal, name of the nonmetal with an IDE suffix, and that's because it is binary, right? Meaning it only has two kinds of atoms in it, aluminum selenide. And even though there's a total of 5 atoms in this compound, right, a unit of this compound, 2 are aluminum and 3 are selenium, it's still a binary compound because there's only 2 of them. All right, so that's what you're going to do on the first set of boxes. Let's walk down to the second set of boxes here. It transfers onto the next page here. Now they're talking about ternary ionic compounds. So let's talk about ternary ionic compounds. All right, ternary ionic are a metal, generally, not always, but 95% of the times you're going to have ternary ionic, you're going to have a metal plus a polyatomic ion. And that's because if you look at your list of polyatomic ions, look at that list right now. I'm going to grab your guys' here so I can use it on the video. If you look at the list of polyatomic ions, are most of the charges positive or are most of the charges negative? Most are negative. There's only one that's positive. What's the one that's positive? Is it listed here? Oh, here it is up at the top. The only one that's positive is ammonium. all these others, all these other polyatomic ions are negatively charged. So since when you're writing nomenclature for ionic compounds, you have to put the positively charged ion first and the negatively charged ion second, a ternary compound is generally composed of a metal and one of those negatively charged polyatomic ions, right? Because the metal is going to be positive, and most of the polyatomic ions, with the exception of ammonium, are negatively charged. Now ammonium, NH4 with a +1 charge, when you have ammonium as a polyatomic ion in a ternary compound, it always has to go first, right? And that's because it's positively charged. Most polyatomic ions, because they're negatively charged, are going to go second when you're using them to name compounds. So if we look at this portion of the table, now what they're asking you to do is the same kind of thing. So now you're going to take the polyatomic ion charge and hook it up with the monatomic ion. So let's go down here to where they're a little bit more difficult. I'll let you guys do the easy ones. And let's look at something like, for example, magnesium and hydroxide. Magnesium and hydroxide. All right, so I've got a polyatomic ion, or a metal. In this case, my metal is magnesium, right? And then my polyatomic ion is hydroxide. Now the charge on magnesium, they tell you on the lab, you also know by looking at your periodic table that the charge on magnesium is +2, charge on hydroxide is -1. So even though it's a ternary compound, the net charge still has to equal 0. So when you put it all together and you crisscross it, it still has to add up to 0. What you have to recognize, though, is that unit, O and H, stick together and they carry that -1 charge. So if I'm going to do the crisscrossing thing here and use them as subscripts, then to write the nomenclature for this particular ternary compound, I would write it as how? Mg, got to put a parentheses, right? Because that is a very different thing than this, right? This tells me there's 1 Mg, 1 O, and 2 H's in that compound, and that compound does not exist, okay? That is incorrect. You have, whenever you need more than one polyatomic ion, you have to put a parentheses around the polyatomic ion and then use the subscript on the outside of the parentheses. Now, let's double check why the charges work here. If magnesium is +2 and hydroxide's -1, right? When I put these two things together, magnesium's +2, I need 2 of those -1 charges. So this half of the molecule is -2 because 2 times -1 is -2. And this half of the molecule is +2 because that single magnesium gives it a +2 charge, right? All right, so what I'm going to have you do now is I've given you the rules for the basics of binary and ternary ionic compounds. Now, in both of these, you do not need to use the Roman numerals. So we're going to add the Roman numerals in the next section. So none of these compounds, none of these need Roman numerals, none of these need Roman numerals, and none of these need Roman numerals. So you can just concentrate on the crisscrossing thing and looking at the formulas for the substances, all right? Then we're going to talk about Roman numerals in the next section. So what I'm going to have you do now is work with the people around you